Hello students, welcome to third session of Ansys Fluent Learn from Home. In today's session, we are going to see the modeling and simulation of 3D fluid flow models. Basically, we are going to take two problems, and so we will, without wasting our time, we will start our today's session. Hello students, in our last lecture, we had seen the problems on two-dimensional fluid flow. In today's lecture, we are going to see and simulate a 3D problem. Okay, so how to do the simulation and how to solve the problem in three-dimensional fluid flow. So without wasting our time, we will click on the fluid flow fluent. Then we will go to geometry and we will select new design model. So our design modeler window opens. So first of all, we will change our unit. So we will change the unit to centimeter. Then we will select the XY plane and we will create a sketch on it. Okay, we will make our weaving plane perpendicular to XY plane. After that, we will go to sketching. In sketching, basically we will solve the problem on Bernoulli's theorem. Okay, basically our aim is to cover the academic portion which we had already learned. Okay, so we will focus on that. So we will take the problem of Bernoulli's theorem. Okay, so we will draw one line. Consider this line. I am drawing horizontally. Okay, after that, I'll give the dimension. Let its horizontal dimension directly general. Let this distance is 0.5 centimeter. And total length is 1 centimeter. 0.5, and this length is 1 centimeter. Okay. After that, we will again go to line. We will select or we will draw one line of increasing slope like this. Okay. After that, again we will go to dimension. We will specify all its dimension. Consider this distance from the center line. It will be 4 centimeter. Okay. Let this distance from center line is also 4 centimeter. Okay. We forgot to mention this distance. So let this distance be 2.5 centimeter. So we will be having a slope of 1.5 centimeter for both the lines. Okay. After that, let this distance from center line and this distance from center line, both this distance be 20 centimeters each. 20 and 20. Okay. After that, we will again go to draw line. We will draw one vertical line. Okay. So whenever the line is vertical, a V symbol will appear. Okay. So we have drawn this vertical line, and then we will close this loop. Okay. So we have drawn one cross section passage of decreasing and then increasing cross section area, or diverging and converging section. Okay. After that, we will go to revolve command. We will use the revolve command. Then we will apply this sketch 1. After that, we are supposed to select the axis. So we will select this YZ axis. Apply. And we are going to revolve it for 360 degrees. So we will go to revolve and we will generate. Okay, so you can see our converging diverging section, it has been created. Okay, now we had made this cross section in XY plane, so we will take another plane. Now consider this XZ plane or ZX plane. So here we will insert one sketch. Okay, after that we will have our weaving plane perpendicular to this sketch. After that we will go to sketching. In sketching we will draw one circle. Okay, we will define its dimension, that its dimension or its diameter it will be 0.6 centimeter. Okay, after that we will create an extrude. Now remember, okay, we will apply this sketch. Now remember, if you are adding the material, if you are choosing the add material, and if you will generate, so basically both of them, both of these bodies, they will automatically unite, and finally you will have a single body. Okay, but I want to create a pattern, so for that I want this body separate. So what I'll do, in this extrude I will change from this add material to add frozen. Okay, so if I am using add frozen, so in that case you can see this body is different and this body is different. Okay, because in comment section some student has asked me why, when to use the frozen body. Okay, so in this way you can make the use of frozen body. After that we will go to create, then pattern. Okay, now we will select our this body and apply. Okay, now I want to give the direction, so let this direction will be YZ. Okay, I want to create, okay, sorry, YZ and then apply. Select this YZ and then apply. Okay, then how many copies I want? I want such 6 copies. Okay, and at what distance? 3 centimeter each. We'll create the, we will have this viewing plane and we will create the pattern or generate the pattern. Okay, similarly again we will go to pattern, we will select this body. Okay, then we will again select this YZ plane, and here now we will reverse the direction and we will create same 6 bodies at 3 centimeter distance each. Okay, so now you can see we are having the 13 manometers, okay, which are at a distance of 3 centimeter each along this length. Okay, now you can see here there are 14 different bodies. Okay, why? Because these bodies are frozen and this is a we had created using material option. Now I want to make this now a single body, so now we can make the use of boolean command. We'll go to boolean, we'll select all these 14 bodies. Okay, and we will unite them. Finally we will have a single body. Okay, so in this way you can model, you can do the modeling of the required problem. So now we will close our design modeler. Okay, after that we will open our meshing tab. Okay, so edit, just click on the edit. We have to wait for some time for the tab to get loaded. Okay, so our tab or our meshing our design model has been loaded here. It will take some time. Okay, so now we can start with our meshing. Our model has been loaded. So we will go to meshing. Then in meshing, we will go to sizing. Okay. Now, first of all, if you want to see the unstructured mesh, you can directly update the mesh or generate the mesh. In 2D model, basically the model is simple, so meshing is done very quickly. But in 3D models, basically there are more number of elements. Okay, so it will take some time to do mesh. So I'm just pausing the video and I will resume it when the mesh is complete. Okay, so now you can see our meshing is done. See, although it is a good quality mesh, you can see here, but it is not a structure mesh, because you can see here there is a more concentration of element on the upper side and less concentration of element on lower side, so it is not a structure mesh. Okay, so there are different methods by which structure meshing can be done. I had already told you meshing is a very big area in which there are different people who are working. It is a big there is a big scope in meshing also. Some people are making their career in meshing itself. Okay, so here we will go to sizing. Okay, uh, here we will see this element size. So our element size is 2.3 into 10 power minus 2. That means 2.3 centimeter. Okay, so we will reduce it to, let's say, 1 centimeter. So maximum size of our element, sorry, it is 1 meter. So it is 1 e minus 2. Okay, so it will become 1 centimeter. Okay, also in quality we will make the quality high. Okay, so now we will update our mesh and we will see how is the quality of the mesh. Okay, I am again pausing the video and I'll repause it when meshing is complete. Okay, so now let's check our mesh. Our mesh is still not so structured. Okay, so now we'll do one thing. We will go to insert sizing and then we will select these edges. Okay, and we will select this edge 1, edge 2, edge 3 and edge 4. Okay, so we had selected these 4 edges. Now we will divide them into, let's say, 100 will be very more quantity. Let's say 60 divisions each. Okay, after that we will again go to insert face mapping, face meshing. Okay, and then we are supposed to select the faces. So face 1, 2, 3, 4 and 5. Okay, and then we will apply. Okay, now we will update our meshing or generate our meshing. Okay, so our meshing is complete now. Now we will see. Okay, now you can see the quality of mesh has been considerably. You can now see there is a uniform meshing near the edges. Okay, so likewise there are different methods by which you can structure your mesh. Okay, more the structured mesh you will have, more will be the accuracy. Okay, so actually meshing is not a part of our session because there are lots of things we can do with the mesh, but we will restrict our meshing till now, and it's almost a structured mesh now. Okay, so now we will define our boundary conditions. Okay, or we will give the names to our boundaries. So let's select this. We will call this as outlet. Okay, so this will be the outlet of water in our case. Okay, then we can define this surface as inlet to the water. Okay, after that we will select this surface, surface 1, 2, 3. Let all this surface. Okay, and let this surfaces also. They are very small surface, so it will take some time. Okay, so we'll name this as pipe or wall pipe. Okay, wall dash pipe. See, always have a practice of defining the wall, whatever the wall surface you are having, with starting with wall, so that the software will already consider this as a wall. Okay, so we are done with our name selections. Okay, so you can see this is our inlet, this is our outlet, and this is our wall pipe surface. Okay, so we will close our mesh. After this step, we are supposed to update the mesh. Okay, so you are supposed to update the mesh, and you are supposed to wait till a green tick appears here. Okay, now so our green tick appears here. So now we can move ahead and we will open the Fluent setup. After that, always remember to click on the double precision and select OK. So it will open up Fluent window. It will take some time. Okay, so it is getting open. Now it will going to recall the mesh. So it will take hardly 20 to 30 seconds to recall the mesh from meshing window to Fluent window. So the mesh has been recalled here. Okay, so now we are having our model. So we can start with setting up the problem again. So first step is defining the model, type of model. So it will be a steady flow. So I'm having a steady model. There is no effect of gravity I am considering. I am considering it is a horizontal flow. Okay. If suppose there is a vertical flow or effect of gravity is there, so you can tick on the gravity and you can specify the value of acceleration due to gravity. Okay. After that we will go to model. Now again here we are having a single phase flow. We are not having any energy transfer or heat transfer, so we will not select here. We are going to see how to use this energy model from tomorrow lecture. Okay. So that we will go to the viscous laminar. Okay. Now by default it will take a laminar flow, but we will change it to K epsilon turbulent flow model. So we had applied K epsilon turbulent flow model. After that we will go to material. In material, air and aluminum are the standard material in the library. We had to recall our fluid. So in our case, our fluid is a water. So we will select this water liquid. Okay, and copy. After that, you can have a aluminum pipe, or if you want to change the pipe material, you can do that. We will take the material as aluminum. After that, we will go to cell zone condition. In cell zone condition, whatever this entire body, which type of fluid will flow, whether it is a solid or liquid. So we will or water is going to flow, so we will take its type as fluid. Now by default it will going to take the air as fluid, but we require the water, so we will change here from fluid to water liquid. After that we will go to boundary conditions. The boundary condition, we are supposed to specify what will be the inlet condition. So inlet condition will be velocity flow. So water will be entering with the velocity. You can give the value of velocity. Let we will define it as 0.5 meter per second because it's a good, reasonable good value of velocity. Then outlet will be a pressure outlet and wall pipe. Okay, the wall pipe, obviously this wall pipe will become a surface. It will not be a fluid. Okay, and its material you can see. If you want to define the surface roughness, okay, so you can define here the value of, suppose the roughness is around 0.25, sorry, 0.002, so it is 2 mm, that is the roughness. Okay. After that, so I think we had said everything, okay, for a fluid flow problem. Then we are supposed to go into solution section. So in the solution section, we are supposed to initialize the solution. So we will use the standard initialization and we will initialize it from inlet. So we will click on the initialize the solution. We have to wait for 2-3 seconds or 5 seconds for the initialization. So the initialization is completed. Now we want to set up the animations. So we'll go to calculation activities, solution animation, double click here. Now you can give the animation name. Suppose I want to I want to see the pressure variation for this flow. After that, okay, after that we will go to contour. Now see, we will see this across any plane. So basically we are supposed to define that plane. So we'll go to new surface and we will define the plane. Now that plane will be along x direction, so its perpendicular axis is z axis. So we will select here a point and a normal, and that normal direction will be 0 0 1. So basically it is perpendicular to z axis. Okay. After that we are supposed to define the, or we will untick here. So basically our axis is fixed now. Now we will define any 2 or 3 points. Okay, so we will say one of the point is 0 0 0. Okay, now basically along z direction all the coordinates will be 0. Okay, now for x1 and x2 we will say let it be 0 0.5 0 0.5 0 0.5 and 0.5 create. Okay, so a plane 4 is created. Now we will see the display of plane flow. Plane 4. Okay, so you can see. Okay, so the plane flow is exactly at the center. Okay, along the x-axis. So we'll select this. We want to have the pressure profile. So save and display. Okay. After that, now see here in animation view, which view you want for the animation. So we will not in need of isometric view. We need front view. So we'll select the front view and we will select OK. Okay. So in this way we have set the animation for pressure. Similarly, we will set one animation for velocity variation. So we can give the name velocity animation. Okay. After that, again, new contour. We'll deselect this. We will take the same plane, plane 4, and we will select here velocity. Okay. So you can see this is the initial velocity. Okay. After that, again, select the contour 2 and set the viewing plane. So viewing plane is front plane. Okay, so we had set this to animation. Okay, after that we will go to run calculations. So we are going to say 300 iteration we are going to calculate. So start the calculation. The calculation has been started. See, this calculation part, it may sometimes take half an hour, 20 minutes, so we had to wait. So I'll pause the video for this process because otherwise it will increase the length of our video a lot. So once the calculations are initialized, they are started, I'll pause the video. It's taking a little bit of time because it is a 3D model. Okay, now you can see this is the animation of, this is the contour of velocity variation, this is the contour of pressure variation, and here calculations had been started. Now right now we are only at our first iteration. Okay, so I am pausing the video and I'll show you the entire animation once the calculations are completed. Okay, so I am pausing the video. Okay, so after 103 iterations, our solution is converged. Okay, so this is our velocity profile and this is our pressure profile. Okay, we will close them because we are will see their animations. We'll go to animation, solution animation playback. Okay, so first of all we will see the animation for pressure variation. Okay, from here we will slow down the speed for better understanding. Okay, so we will play the animation. So you can see initially the solution was not converged. Okay, so you can see some red lines here and there. Now see, the solution starts to converge. Okay, so you can see here, this red line indicates higher pressure region. Okay, now you can see, although this cross section area and this cross section area is same, but here the pressure is more. So that means when the flow is taking place from this cross section area, so to the same cross section area, there is some loss of pressure which is taking place along the length. Okay, and you can also observe in the direction of the flow, this pressure is reducing from red to yellow, yellow to green. Okay, green to light blue, and so on. And when the area is increasing, okay, then in that case the pressure is again increasing. So this was a pressure animation. Now quickly we will see the velocity variation or animation of velocity variation. Okay. So play the video. So you can see, so you can see how the flow is taking place. Now see, all these manometers, they are blue because flow is not actually taking place across the manometers. Okay, the flow is only taking place across this section. And you can see here the red region indicates higher value of velocity, where the area is minimum, velocity is more. And here the area is more, so here the velocity was less. So you can see the velocity is increasing from blue region to green to yellow to red, the direction of flow, and the area is reducing. When the area is increasing, this velocity is reducing. Okay, but the velocity has a constant value away from the surface region towards the center. That means the velocity is increasing as you move, as you are moving away from the pipe section. So I think this animation explains almost every concept of fluid mechanics which you had learned in fluid dynamics. Okay, so we will close our flame. We will go to our CFD post. It will take some time to close this Fluent because all these files, they are being written into a temporary folder. So we have to wait 5 to 10 seconds. Okay, after that we'll go to CFD post. Okay, and we will select the edit. So CFD post window will going to open. Okay, so our CFD post window is open now. Now first of all, see, it is a 3D model, and if you want to see the result in or you want to convert this problem of 3D model to 2D model, so you are supposed to insert a plane. So we'll insert one plane, and that plane will be along XY axis, XY plane. Okay, so XY plane. Now I'm keeping the distance 0 because I want exactly on it on x-axis. So we'll apply it. So you can see a plane is created exactly along the XY plane. Okay, so if you don't want to see this plane, you can untick here. Okay, so that plane will not be visible. Then we will go to contour. Okay, in contour, you can select the location where you want to see the variation. I want to see the variation along plane 1. That will be for pressure variation, and here you can give the number of divisions, number of contours. Okay, let's say 100. Okay, so you can see here it will going to show me whatever the pressure variation which is taking place along the length. Already we had discussed, here the pressure is more. Okay, pressure is decreasing as the area is reducing. Here the pressure is minimum at the point where the area is minimum, and then the pressure is increasing. And again, although this inlet and outlet cross section areas are same, but here the pressure is not there. That means there is some loss of pressure which is taking place along the length. Okay, then if you want to see the velocity variation, so select the velocity. So this is the velocity variation which is taking place. The velocity is increasing as the area is reducing, it is maximum near the surface or region where the area is minimum, and then the velocity was also increasing, but it is uh, not up to the value which was at the inlet. Okay, so you can clearly see how the flow will take place when the expansion is taking place. Okay, after that we will untick this contour and we will go to streamlines. Okay, after that which type of streamline we want to see? We want to see first of all surface streamline. On which surface? On plane 1. Okay, uh, let it be 50 lines, 50 streamlines flat. So you can see these are the streamlines. Make it from inlet. Okay, on plane 1. Suppose we will make it 200. So you can see these are the streamlines. Okay, don't bother about this because here the fluid is stationary. Okay, in the manometers. If you want to see its animation, you can go to animation and you can play this animation. Okay, sorry, you are supposed to select this streamline one. Streamline one. Then one. Play. Okay, we'll stop here. Now, see, basically the fluid is flowing and the variations are almost color is showing the variation, so it is not showing the fluid particle here. So for seeing the how the actual fluid is flowing, we will see this 3D streamline. Okay, and we will apply this 3D streamline and we will start from inlet. So we have to change this. Okay, start from inlet. Okay. So now you can see in YZ plane, in XY plane. Okay, now we will see its animation. Okay, we will slow down its speed. Okay, now we will play. Now you can see the fluid is coming slowly as the area is reducing, its velocity is increasing. Okay, we will stop here. Then we will change the viewing plane. Let's say I want to see this animation along XY plane. Okay, so we will go to again animation and you can see here how the flow is taking place. Okay, okay. So I think how to set up the animation, uh, it is understood to you. So we will untick here. Okay, now we will insert one line exactly at the center. We will go to location and line. Okay, let it be called as line 1 and we are supposed to define its coordinate. Again we want to draw it along xy plane, so z coordinates are 0. We are supposed to define the uh, end coordinates. Okay, so we will say let x1 coordinate will be minus 0.25 and y coordinate is 0 and for 0.2 it is 0.25. Okay, so minus 2. Minus 0.25, that means 25 centimeters 0 0 and plus 25 centimeters 0 0, and I'll apply the line. So you can see on both sides this 5 centimeter line is going outside because the length from the center was 20. So I'll make it to 20 and 20. Okay, and you can see the line is completely covering the our passage flow. Okay, flow passage. Now we will go to chart. Okay, we will go to this chart, insert the chart. Now insert in chart, we will go to uh, where you for what location you want this chart. I want it for line 1. What you want along x-axis? Okay, forgot to cut the sample size. So basically by default it take uh, 10 sample size. We will make it to 100. Okay, apply. That means the entire passage is divided into 100 divisions. Okay, then we will go to chart again. Okay, select the chart. Okay, then data series, location line 1. Then what we want along x-axis chart, which is 100. What we want along y-axis pressure. Okay, apply. So you can see along the length from 0 centimeter we had divided into 100 parts. So along the length it was reducing, it become almost negative. Okay, near the region where the area is minimum, and then again it is increasing. Okay, now at the inlet and outlet the areas are same, but you can see there is a considerable drop in pressure. Okay, similarly we can see the velocity profile. Okay, so you can see the velocity was increasing, okay, as your section area is decreasing, and then it decreases, okay, as the value area increases. So I think that much will be for this problem. Then we are going to take another problem of 3D section where we will try to cover 2 problems in this section. So I'm closing the CFD post. So we will start with the second problem which we are going to take today. Again, we are going to take the problem from academics. We are talking about the fluid flow. So we'll take one problem for fluid mechanics, and that problem will be for Orificemeter. Okay, so we will click this fluid flow. After that, right click on the new design modular geometry. We have to wait till it gets open. Okay, after that, first of all, we will change the units to centimeter. After that, we'll select the XY plane. We will make a sketch on it. We will make the viewing plane normal to it. Then we will go to sketching. In the sketching, we will first of all draw one rectangle like this. Then we'll go to dimension. In the dimension, we will specify its distance from the center. This distance. So let this distance h1, it is 0.25. That means 2.5 mm. Let this distance is 0.5 centimeter. That means 5 mm. Okay. After that, let this height be 1 centimeter, and the distance of this rectangle from the center line, that is also 1 centimeter. After that, we will go to line, draw a line, some inclined line like this. Then again dimension, will specify the position of this top edge. We will say this is 1.2 centimeter. After that, we will go to modify, trim, and we'll trim this section, this section, this section, and this section. So basically, we will have a cross section of the orifice. Okay, edge-shaped orifice. So we will go to create, revolve. We will apply our sketch as a geometry, and we will select the axis as YZ, and we will change this add material to add frozen. Okay, and then we will generate. So this is our orifice. Okay, after that we will select the normal plane. Let that normal plane will be YZ. So we will draw one sketch on YZ plane, and we will go to sketching. In the sketching we will select a circle coinciding with the origin. Okay, now this distance was 1 centimeter and this was 1, so actually the radius is 2 and diameter is 4. So we'll go to dimension and we will specify the diameter as 4 centimeter. Okay, so basically it is exactly matching with our orifice. Okay, after that we will go to create, extrude, and we will select both side extrude, both sides symmetric, and let the length be 20 centimeter. Okay, let the length be 20 centimeter, or let it be 25 centimeter. I think 20 is fine. Okay, 20 centimeter, and we will generate it. Okay, so now you can see there are two bodies. This is solid body and this is our pipe surface. Okay, but remember they are overlapping. That means if you unhide this, so basically pipe is a straight circular pipe. So basically we are supposed to subtract this orifice surface from pipe surface. We'll go to create and boolean. Okay, in boolean we will subtract. Now what is our target body? Target body is our pipe surface, and what is the tool body? Tool body is our orifice. Okay, and whether we want to preserve the tool body, yes, we want to preserve it. So we will generate. Okay, so now see, if you hide this orifice body, so this is now the passage of pipe or passage of fluid which will flow, and if you show this, so basically that will be our orifice plate. So we'll, for simplicity, we will name it as orifice. Okay, so it will be easy for understanding. Okay, so now we will close our, we had done the modeling part, so we will close our design modeler, and we will go to sketch, sorry, we will go to mesh. So click on the edit mesh. Okay, so our model is being uploaded here in the meshing window. We have to wait for 5 to 10 seconds. Okay, so our model has been attached now. So again, if you want, you can simply see what will be the nature of meshing which will get by default setting. So it is an easy model as compared to our previous models. You can see here all very good quality of mesh is there, but still it is not that much accurate. Okay, so we will first of all reduce the element size from 2 centimeter. In the default is 2 into 10 power minus 2, so 2 centimeters. So I'll reduce it to 1, so 1 e minus 2, so it will become 1 centimeter. Okay, after that we will go to sizing. We will select the edges, edge 1, 2, 3, 4. Okay, apply, and we'll map that. So insert face meshing. We'll select all the faces 1, 2, 3, 4, 5. Okay, apply, and then we will see what is the quality of mesh now we will get. Generate mesh. Okay, it's a good quality mesh. You can see the element size is still bigger, so we will again reduce it to 5 mm, 0.005. Try to update it. Generate mesh. Okay. Now it's a good mesh, quality mesh. Okay, so after so our meshing is done. So now we will define our boundary conditions. So let this be outlet of the file. So create name selection and we'll define its name as outlet. Then again this will be create name selection in. After that you can define this surface and this surface. Okay, create name selection. This will be pipe wall dash pipe di. Okay. Now I am hiding this constant for this solid hide body. Now you can define this surface point 2, 3, 4. Create name selection wall dash orifice. Wall orifice. Show this body. Okay. So we had given almost the name outlet, inlet, wall, pipe, and wall orifice, and defined each surfaces. So now we will close our meshing. After this, we are supposed to update the mesh. So we will go to mesh and we will update it. We have to wait till a green tick appear here. Okay, so now you can see green tick appear. So we will set up the problem. So we go to Fluent setup. We will click on double precision and OK. It will take some time to open the Fluent window. So our meshing is being included here. So we can wait for 5 to 10 seconds. Okay, so you can see the mesh has been uploaded here. Again, first step is the which type of model you want. So we want study model. Okay, then which energy model basically required in heat transfer, so we'll not apply that. We'll go to viscous and we'll change this laminar model to K epsilon. Select OK. After that, material. Again in material, the default material are fluid and air and aluminum. So we will go to fluid database and we will add water liquid. Okay, so you are supposed to just click on the copy. You can see here water liquid has been added to material library. Then we will go to cell zone condition. So there are two cell zone condition. First is orifice. So orifice is not a fluid, orifice is a solid. So we have to define it and let its material be aluminum. If you want, you can make it steel, okay, by adding it from material library. And this solid. So basically solid is a fluid, but by default it will take it as air. Okay, so we are supposed to change that air to water liquid. So now we have defined the fluid material. We will go to boundary conditions. Okay, now see here, this is our inlet. It is a velocity inlet. We are supposed to give the value of velocity here. So we will define its magnitude. Let's say it is 0.5 meter per second, which is a reasonably good value. Outlet is a pressure outlet. Then this pipe wall, it is almost a wall. Okay, so nothing to change in it. If you want, you can define here the surface roughness if you want. Okay, so from here you can give the surface roughness that it will be 0.002, that means 2 mm. Then mesh interfaces, nothing to do with that here. Okay, after that, next is solution. So in solution, we are supposed to initialize the solution. We will initialize it from inlet. Okay, so initialize it. After that, in calculation activities, we will see the animation of how the flow is taking place and pressure variation is taking place. So we'll set the pressure animation and we'll go to new object, contour. In the contour, we are supposed to uh, make a new plane, a weaving plane. So again, we'll go to point and a normal. Basically, our plane should be normal to z axis. So here we will make this x component 0 and z component as 1. So it will be 0, 0, 1, normal to z axis. Okay. After that, about which point, basically all the z coordinates will be 0 for our case. So it is 0, 0 and 0. Okay. Then let this coordinates be also 0. Okay. Then we will define this. I think the length was 20 centimeters, so it is 0 0.2. Let this also be 0.2. Along x-axis, let it also be 0.2, 0.2. Create. So the plane 12 has been created. We will display this plane 12. Okay, so you can see this is a plane 12 which is passing almost across xy plane. Then we want to have the pressure animation, so save and display. Then select the contour and we will change the weaving plane to front plane. Okay. Similarly, we will set one animation for velocity. So we will give the name velocity to that animation. Again, new object, contour. We want it for plane 12 and the property which we want is velocity. Okay. Forgot to select the contour. Select the contour and then set the weaving plane as front. Velocity. Okay. After that, we will go to run calculation and we will see 150 iterations first. So basically the calculations has been started, the iterations calculation has been started, but basically it will take some time. I am going to show this animation. Okay, so I am pausing the calculations. Okay, and once the calculations are done, I'll resume the video. Okay, so our 150 iterations are done, but solution is still haven't converged. So I am again giving 150 iterations. So that iteration will add from 151 onwards. Okay, so now you can see after 179 iterations our solution is converged. Okay, so we had got the converged solution. So quickly we will see the animations, how the flow, pressure variation and velocity variation had taken place along the length. So first of all we will slow down its speed something here. We will first of all see the pressure animation video. So you can see before the pipe the pressure is almost constant. Before the orifice the pressure is almost constant. Okay, and after the orifice the pressure is continuously it is less than what is at the inlet. Okay, so here the pressure is almost constant, but that pressure is less than what at the inlet. That means some loss of pressure is taking place. Okay, because the before orifice and after orifice the pressure values are different. And we will see the animation for velocity. Okay, so now you can see when the flow is taking place, okay, in this region basically the velocity suddenly increases. Okay, so first of all, contraction is taking place, so velocity is increasing, and then the expansion of the jet is taking place, so velocity is again reducing. And this blue region indicates there are some region where the fluid is trapped and that fluid is not flowing. Okay, there will be whirling motion around there, and that is almost similar to stationary fluid. Okay, so this is a very good animation to explain you the physics behind the contraction and expansion when the fluid flow is taking place around the orifice. Okay, so we close our Fluent and we'll go to CFD post. Okay, so we'll right click here and we will select the edit. Again, we have to wait a while. Okay, so now you can see our CFD. Now you can see our CFD post window is open now. Okay. Again, we want to add a plane. So we'll go to location, plane, and that plane will be along XY plane. So apply. Okay, so now you can see this is a plane 1. Okay, after that we will go to contour, select the contour. You can unclick this plane. Okay, after that we will select the plane 1 and we will define the number of contour to, let's say, 100. Okay, and apply. So you can see here what is the pressure variation that is taking place. Okay, so pressure is very high before the orifice, then suddenly there is a drop in pressure. You can see in this region the pressure is minimum. Okay, and then this pressure value again increases. Okay, in this region it is again less, and in the direction it is increasing, and then that pressure is constant. Okay, after that we will see the velocity contour. Okay, so now see, you are seeing the disturbances here. Okay, so that disturbances is because we had given the surface roughness. So if you had assumed it as a smooth surface, so these disturbances would not be there. It will be a blue straight line. Okay, now you can see here how the flow is coming out as this area suddenly reduces. Okay, so the velocity suddenly increases in this region. So you can see this region, then the flow come out in the form of jet. Its area first of all reduces and then increases. And in this blue region, some fluid is trapped. Okay, some whirling motion is taking place in that. Okay, now you can see here the pattern is not that much clear. This is because we our these regions we are getting because of meshing. Okay, more the structure mesh, more accurate result you will get. Okay, so this indicates our meshing is not of that much good quality, but it's okay for learning purpose. Okay, then we will go to streamline. Okay, first of all we'll untick the contour, otherwise it will overlap. Then we'll go to streamline. Okay, then first of all we'll see the surface streamline on plane 1, like 50 streamlines. Okay. I had told you, or let it be, we'll say 100. Okay, so as mentioned, as I mentioned you, some quantity of water has been trapped, and that water was having a whirling motion, and it is almost stationary. You can see here. Okay, and you can see the streamline, how the flow is taking place. Okay, after that we'll try to see its animation. Okay, so this is how the flow is taking place along the XY plane. Okay, so we'll stop the video, then we will go to 3D streamline. Okay, and we will start from inlet. Okay, so this is our 3D streamline. Okay, you can change the viewing plane also. Okay, then we will go to animation, and we will play this. So you can see how the fluid is coming. Okay, suddenly its velocity increases in this region and then it again decreases. Okay, after that, if you want, you can again see the velocity variation along the graph. So we'll untick this. We will again go to location line. We'll insert the line. I think the length along x-axis was minus 0.2, that means 20 centimeter, and plus 0.2. Okay, so we'll apply here, so you can see the line appears here. Okay, after that we will go to chart. Okay, in the line we will make the or divide it into 100 samples. Okay, then we will go to chart. Then in the chart data series, here we will select the location as line 1. Along the x-axis we want chart count, along the y-axis we want pressure. So you can see this is the pressure was almost common. It was a little bit decreasing due to frictional losses. Then suddenly the pressure drops, and then the pressure rises, and whatever this difference, it indicates the minor loss. Okay, due to sudden contraction. Similarly, for the velocity, you can see the velocity suddenly increases and then it decreases, and basically we are not getting the smooth curve because the quality of meshing is not that much good. Okay, but for running purpose it was okay. Okay, so in this way we had completed our second problem. So in today's session we have seen the two problems on 3D fluid flow. In tomorrow's session we will start with the problems of heat transfer. Thank you for attending the session, and have a nice day. Stay safe.